Namaskar and welcome to StudyIQ. I am your friend Rahul Saigaonkar. Let's continue our discussion of NCERT Science series. You all know that very recently we started with the NCERT textbook for class 10. And here also we are following the similar format that we followed with class 6, 7, 8 and 9. That means we are going to discuss this textbook chapter by chapter. And till now we have completed two chapters, chapter 1 and chapter 2. And by now you must have understood that we are into advanced science discussion. That's why the classes are also going to be a little lengthy. So get ready for a long haul. In the latest discussion, we discussed chapter 2, acid, bases and salts, and our focus was predominantly on these salts, where we discussed salts or chemical compounds that we use in our common day-to-day life. We spoke about washing soda, baking soda, bleaching powder, plaster of Paris, so many things. Today we'll move ahead and continue our discussion of chapter 3. Now chapter 3 deals with metals and non-metals. Now regarding this, we already have some amount of basic knowledge from our previous class discussion, because we have already understood characteristics of metals and non-metals in the discussion in class 9. So we will be building up on that. Of course, I'll be giving you a small recap regarding that as well, and then we'll move ahead into this particular chapter. So let us begin. As I told you, metals and non-metals, we have some idea about these from class 9 discussion itself. What did we discuss in class 9? We said that when we look at the periodic table, we can see that there are metals, there are non-metals, and there is another class of metalloids, although this is not mentioned in the NCERT, but I had given you this input in our previous discussion as well. So metals are these which are represented in the red in periodic table. Non-metals are the ones which are represented in blue: hydrogen, helium, carbon, nitrogen, oxygen, fluorine, neon, phosphorus, sulfur, chlorine. These are non-metals. And there is another class which is called as metalloids, which fall somewhere in between these two. And we have discussed that metals are those elements in the periodic table which are characterized by similar traits. Metals are typically hard. Majority of metals are solids. They are lustrous and they represent or they give certain similar characteristics. Approximately about 90 types of metals are found in the periodic table. Apart from that, non-metals are the ones which are characterized because of their lack of metallic properties. They are generally non-solids. Even if they are solids, they are brittle in nature, and their properties with respect to electricity are poor. They are poor conductors of heat as well as electricity. We also discussed that non-metals, generally we categorize them into three categories. Non-metals like elements like sulfur, phosphorus, carbon, halogen, chlorine, bromine, fluorine, etc., and noble gases. Noble gases, that is helium, neon, argon, etc. There are about 20 non-metals that we find in our periodic table. Apart from these two, metals and non-metals, just for your information, we also have few elements that are characterized as metalloids. Why? Because their characteristics are somewhere in between metals and non-metals. The classic example being semiconductors that we use in our electronic industry. Some of the examples are silicon, germanium, etc. So metalloids are the ones which have characteristics between metals and non-metals. This we have already established, and we also discussed some of the characteristics. Metals versus non-metals. When we see metals are lustrous, they generally form cations, that means positive ions. Non-metals, they generally form negative ions. And metals are more lustrous, they are good conductors. The opposite side you'll find non-metals. We also discussed some of the characteristics in details. So how do we put metals in a category? Because they show similar kind of traits. For instance, metals show heat resistance. That means they have high boiling point and high melting point. Metals show good properties towards electricity and heat. That means they are better conductors of heat as well as electricity. They conduct heat and electricity through them. That is why most of the metals are solid and most of the metals are dense. Some of the exceptions can be like mercury, but majority of the metals, they are dense solid materials. Non-metals are generally gaseous. Even if they are solids, they are brittle. Apart from that, metals exhibit two important properties, very important: malleability and ductility. Now, malleability is a property of metal by virtue of which we can simply transform them into sheets. That means you can hammer them continuously and you can bring them in a shape like a sheet. Ductility is the property of metals in which you can you can heat them and pull them and create thin wires out of it. Now, what wires do we use in our electrical equipment? It's copper. What is copper? Copper is a metal. For example, gold. You must have seen gold ornaments, right? Very costly. It is said that a single gram of gold, it can be pulled into a wire which can elongate up to 2 kilometers. Unbelievable, right? It's actually true. A single gram of gold can be elongated or created into wire which would be about 2 kilometers long. So they have ductility. They show malleability, they show ductility. Majority of metals are also lustrous. That means they have shiny and metallic appearance. And since they have ductility, malleability, and they are lustrous, they are also sonorous, meaning they create sound. Have you heard that sound? When a metal, say simply, if you let a ring slip out of your hand and it falls on the ground, it makes a sound, and that sound is stinging. That sound is sonorous. So that's why metals are sonorous. They ring sound. Apart from this, as I told you, they're already dense. Their physical form is mostly solid at room temperature. Exception is mercury for sure. Apart from that, metals form alloys. Metals can be mixed together to get alloys. And when they ionize into cations, that is positive ion. Classic example, Na plus, right? Sodium plus. They ionize into cations. Now, on the opposite end is the non-metals. Non-metals will have poor conductivity with respect to heat and electricity. They will not have that heat resistance. That means they will have low melting point and low boiling point. They do not conduct electricity and heat. They are not dense. They are not hard. Even if they are solids, they would be brittle. They would not be lustrous. They lack that metallic shiny appearance. And of course, they would not be sonorous as well. Apart from that, as I told you, density would be lower. And when they ionize into negative ions. Again, classic example being Cl minus. Why I give this example? Because we use NaCl every day. That is common salt, sodium chloride. Na plus, Cl is minus. So metals, they form cations, and non-metals, they form anions. So these are some basic characteristics of metals and non-metals. Again, this has been repeated in the chapter. We have discussed that before also in our class 9 interaction. But let's move ahead and talk about some technical stuff specially connected with metals from this chapter. But before that, there is a small notice for all of you. If you are preparing for UPSC Civil Service examination, then the 12th July batch is already closed out for you. And if you missed out on that opportunity, then you have another opportunity to join our P2I initiative. StudyIQ is giving prelims to interview initiative, where we will be handholding you through prelims, through mains, through interview. We have created a comprehensive and integrated program where we will be preparing you for all the 3 stages. And we are offering this in 3 formats. It is available in English, Hindi, and in a bilingual format, English plus Hindi. That means the content and the delivery would be in these formats. You do know that StudyIQ has a motto of taking education to everybody. We have a motto of affordable education for all. That's why these courses are priced at an optimum range. And if you want maximum discount on these, you can always use my code Rahul Live. Whenever you check out, use this coupon code. Remember, our batch is starting 22nd July and at 6 p.m. This is the evening batch, not the morning one. So please join. I'll see you in the class. All right, let's move on. Till now, we discussed physical characteristics of metals and non-metals. And in this discussion, we'll be focusing more and more on metals itself. And now let's talk about chemical properties. What are the chemical properties of metals, and some discussion about non-metals as well. First thing, what happens when a metal is burnt in air? Now we have already understood what is the composition of air. The composition of air is, there is nitrogen in it, 78%. Then there is oxygen in it, 21%. Nitrogen is rather unreactive. So what will happen when we burn metal in air? There is oxygen which is reactive. So metals, except for noble metals like gold, silver, platinum, with respect to other metals, what they do is they react with oxygen in the air. When we provide heat, when we burn these metals, they react with oxygen to form metal oxides. And we know from our previous interaction itself, metal oxides are basic in nature, right? Metal oxides are basic in nature. And these reactions are exothermic. That means when we burn them, more and more amount of heat is also released. Some of the examples can be given here. As I told you, metal plus oxygen, it leads to creation of metal oxides. Classic example, copper. Copper, when you burn in air, it reacts with oxygen to give you copper oxide. Similarly, aluminium, when you burn in air, it reacts with oxygen to give you aluminium oxide. And I told you that generally metal oxides are basic in nature. And now by now I already understand, if metal oxides are basic, when they react with your acid, they neutralize. This we have discussed before also. But there are some metal oxides, predominantly like aluminium oxide, they have peculiar behavior. Sometimes they act as basic and sometimes they also act as acidic. Some exceptions like aluminium oxide. But generally metals, when they react, they form metal oxide, which are basic in nature. Again, depending on the reactivity of the metal, some metals react fastly, some metals react slowly. Next, what happens when metals react with water? Metals, when they react with water. Now, we understood metals when they react with air, that means with oxygen, they form metal oxide. In water also, water's chemical formula is H2O. Means when metals react with water, they are going to react with oxygen as well. So a metal oxide would be formed. But since there is water present, that means water amount is high, then that metal oxide is going to further react to form metal hydroxide. So remember, some metals do not react with water. Again, classic example being gold, silver, etc. But many metals, they react with water to form metal hydroxide. Again, depending on the reactivity of that particular metal, some react very vigorously. Some react vigorously, releasing heat, giving some sort of precipitation. For instance, sodium, potassium, they readily react with water. Whereas magnesium, it does not readily react with cold water. But if you provide hot water, it reacts. Metals like iron, they react with water very slowly. They corrode slowly. So what happens when metal reacts with water? A metal reacts with water. It first forms metal oxide, because water also has oxygen, and it releases hydrogen gas. How do we get this, or how do we sense this hydrogen gas? We simply burn it. A pop sound comes out. Then this metal oxide, it further reacts with water to give you metal hydroxide. So we already know that when a metal oxide is formed, this metal oxide is basic in nature. And if we have this metal oxide in water, it will give you metal hydroxide, meaning it will give you a basic solution, a basic aqueous solution. And if it completely dissolves in the water, it becomes an alkaline solution, because we discussed what is the difference between alkali and a base also. Classic example being here. Now take potassium, take sodium, add water into it. They react with water very vigorously to form these hydroxides. Next, how do metals react with acids? How do metals react with acid? Now we have already discussed this when we spoke about acids and bases. When metal reacts with acid, they produce a metal salt and they also release hydrogen gas. Right? Now, for example, let's take, say, sodium. Right? Sodium plus you take sulfuric acid. Now what is going to happen? The product would be, we have sodium sulfate, you have a sodium sulfate, right? And then you have hydrogen gas. Of course, this is not a balanced reaction, but just for your understanding, I'm telling you that sodium sulfate is formed, Na2SO4, and then hydrogen gas is released, right? So this is a classic idea of metal reacting with acids. Now, we have also seen that with some acids, hydrogen gas may not be released. Please remember this. So general reaction is when metal reacts with acid, they produce metal salt, one particular salt, plus hydrogen gas is released. How to sense that hydrogen gas? Simply burn this hydrogen gas, a pop sound will come when you burn it. But there are some acids with which hydrogen gas may not be released. With some particular metals, hydrogen gas is not evolved, especially when metals, they react with nitric acid. Now, when this happens, the products would be, of course, a salt, then you get water, and then you get nitrogen oxide gases are also released. Nitrogen oxide gases are released. There is one exception, magnesium, when it reacts with nitric acid, it also releases hydrogen gas. But please remember, when metals react with HNO3, nitric acid, the nitrate oxides or nitrogen oxides are released. All right? Right. Next, how do metals react with the bases? Now, please remember, when a base reacts with a metal, it leads to formation of a salt along with liberation of hydrogen gas. This we have already established. So metals, they react with bases to produce hydrogen gas and a salt, very similar to how we have seen with acid. But when it comes to non-metals, non-metals do not generally have such a simple kind of reaction. It is much more complex. For example, say when bases react with non-metals like carbon dioxide, it leads to formation of sodium carbonate and water, one of the examples, but the interaction can be a little complex as well. So metal reaction with the base, again, similar to acid, it gives a salt and hydrogen gases released. Next, how do metals react with solution of other metal salts? Now, we know that metal salts, if they are able to electrolyze, then electrolyte is formed. Now, in such a reaction, in such a aqueous solution of metal salt, do other metals react with it? Now, this depends on the reactivity of metal. Here comes the concept of reactivity. Now, in our previous interactions, we have discussed two kinds of reaction. One was the neutralization reaction. This was very simple. Acid and a base mixing leads to salt and water. This we have discussed. We have discussed another reaction called as displacement or replacement reaction. Replacement meaning one metal replacing another. And we have also discussed two kinds of displacement or replacement reaction: single displacement, double displacement. But this displacement, it depends on the reactivity of metal. So when a metal reacts with a salt solution of another metal, when metal A reacts with salt solution of metal B, depending on the reactivity of that metal, the metal A can replace metal B in the salt solution. And this is called as displacement reaction. But again, this depends on the reactivity of the metal. I'm putting a condition here. It depends on the reactivity of metal. For instance, if you just look at this particular picture, you'll understand that there are two test tubes. In one test tube, there is copper sulfate solution and an iron nail. And you see there is no displacement here. That means iron is not displacing copper. But in another test tube, you have iron sulfate solution and a copper wire, and you see slowly and steadily something happening to copper. Now, when you look at this, what happens? Why there is no displacement? Because it depends on the reactivity, and this is the reactivity series for the metals. If you look at reactivity series, potassium is highly reactive. Now, in this sequence from the NCERT itself, in this sequence, the top ones are the most reactive, meaning if I take potassium and I put potassium in sodium salt solution, then potassium is going to replace sodium. But if I take sodium and put it in potassium based salt solution, sodium cannot replace, right? Meaning the upper one would replace the lower one. This is the reactivity series. The most reactive is potassium, and in this sequence there is also mention of hydrogen here. You must be surprised, sir, in this series of metal, why we have put hydrogen here? Hydrogen, it becomes a reference point. Hydrogen also has some sort of reactivity, because you do know hydrogen, it consists of one proton, one neutron, one electron, and since there is one electron, it tends to lose that electron and react quickly to form H plus. We have seen this. That's why it is also included in this particular series. And you can see at the bottom, you will find noble metals like gold, silver. So gold, silver, they do not react. Platinum does not react. Mercury has very low reactivity. Copper has less reactivity. Copper can react. In fact, for your reference, I have created a chart here which you can refer. I'll be sharing this PDF. You do know that I do share these PDF at my Telegram channel itself, which goes with this particular ID, Rahul SAI222. You can always take the reference from here and look at this particular sheet. For your reference, I've put this, that most reactive metals like potassium, sodium, lithium, barium, strontium, calcium, these are most reactive metals. They react even with cold water. But below that, magnesium, beryllium, aluminum, titanium, magnesium, they need heat. That means they may react with hot water, they react with acids. You just go below and you'll find you need stronger acids for reactions. And for silver, gold, they do not react. They are highly unreactive with even strong oxidizing acids as well. All right. So this is the reactivity series. Now, apart from this, there is one more idea. How do metals and non-metals react? Let's talk about reaction between a metal and non-metal. I'm not talking about metal oxide, non-metal oxide. Directly, reaction between metal and a non-metal. Now, we have already established that metals, when they are ionized, in their ionized state, they tend to become cations. And non-metals, they tend to become anions. That means there is bound to be some sort of interaction between these positive and negative ions. That is what we can see from this particular chart. Now, we have discussed in our previous interaction also the concept of octet. Now, what is this octet? Octet meaning having or complete fulfilling of 8 electrons in the outermost shell of a metal or a non-metal. Now, if you look at the electron configuration of some of the gases, some of the metals, gases and non-metals here, noble gases like helium, neon, argon, they seldom react. Why? Because their outermost shell, it fulfills the criteria of octet. For instance, helium, it has only 2 electrons, so 2. If you look at neon, it has 2 electrons in the innermost shell and the outermost shell has 8 electrons. That means the octet is complete. That's why its reactivity is very, very low. Similar case with argon. Argon, 2 electrons in the innermost shell. In the next shell, that is L shell, you have 8. In the next shell, the outer shell, in the M shell, you again have 8. That means you have completed the octet. So its reactivity would be very, very low. But if you look at other metals and non-metals, you will understand that they react on the basis of stability, reaching towards that stability. Now, if you look at a classic reaction between sodium and chlorine, you will understand that for sodium, if you look at its electron configuration, sodium, the atomic number is 11. So it has 11 electrons, 2 in the innermost shell, 8 in the outer shell, and in the outermost shell, you have only 1 electron. So sodium, to achieve that octet, either it needs 8 electrons, then the octet would be achieved, or it is very easier for sodium to simply give out that 1 electron. It will reach the octet level. So what is the best likely possibility? Better sodium loses 1 electron. So which is the candidate which I can find here, which has 7 electrons in this outermost shell? Now for this chlorine, what would be a better probability, right? Losing out 7 electrons or accepting 1 electron to achieve that octet. That is why you see a reaction between sodium and chlorine. And in their ionized form, we get ionic compounds. So how do metals and non-metals react? By sharing the electrons. That means in the ionic form, they lead to formation of ionic compounds. Classic example being sodium and chloride. So what does a reaction between metal and non-metal lead to? They lead to creation of ionic compounds. What are these ionic compounds? Ionic compounds are pure substances formed by reaction between a metal and a non-metal, where they tend to reach a stable phase, where they have chemically bonded, where there is some sort of ionic bonding between these two ions, between the cation and the anion. Now, when we talk about ionic compounds, it can be between a metal and a non-metal, or it can be polyatomic also. There can be different atoms. For example, here sodium sulfate, right? Sodium sulfate. That's why Na2SO4. I told you it is not balanced. Na2SO4. So oxygen, sulfur, and sodium are all three are combined here, right? Ionic compounds. Now, what are these ionic compounds? In our day-to-day life, we use so many ionic compounds. Let's try to understand some of the characteristics of these ionic compounds. Ionic compounds, in their physical form, they are solids. Generally, they are solids and they are hard. Remember, they are not malleable, they are not ductile. they are generally brittle in form. Classic example, NaCl, salt. Can salt be molded? No. Can salt be extended into wires? No. It is simply brittle. It consists of positive and negative ions. Apart from that, if you look at its chemical properties, the ionic compounds, they have high melting points and high boiling points. Why? Because they have reached a point of stability. Now, to break them, I need to give too much of energy to break the bond between them. The ionic bond breakage, it needs a lot of energy. These are some of the exercises that you can carry on to understand what are the properties of ionic compounds. Classic being salt, NaCl. See, if you look at the melting and boiling point of NaCl, sodium chloride, 1074 Kelvin, it is the melting point, and boiling point is 1686 Kelvin. Same is the case with lithium chloride, calcium oxide, if you look at these ionic compounds. So ionic compounds in physical nature, they are solids, they are brittle. Chemically, their melting point and boiling point is very high. They are soluble in water. Now just try to conduct an experiment. We get all these things at home. Okay, do one thing. Take pinch of salt, mix that in water. Of course, it will dissolve. That means we already know salt dissolves in water. But take same pinch of salt and take a little bit of petrol. Don't take petrol. Petrol has become quite costly. Take a little bit of kerosene if you find. Okay, mix salt in kerosene or petrol. See if it dissolves. Try to stir it. Will it dissolve? It won't. So you'll understand that their solubility is high in water, and they are not soluble. They are seldom soluble in kerosene, petrol, etc. Apart from that, when you create this solution, you do know this solution can become an electrolyte. That means they conduct electricity in their aqueous form. That is why we have seen in our previous interaction also, from a simple brine solution. What is a brine solution? Brine solution is concentrated NaCl solution. From a simple brine solution, we can get so many different compounds, so many different chemical compounds, so many different salts which we use in our day-to-day life. So ionic compounds, physical properties, chemical properties, solubility, and conduction of electricity, that we need to know. From exam perspective, it becomes important. A simple kind of MCQ can be created. Consider the following statements about ionic compounds. First statement: generally, ionic compounds have low melting point. Second statement: ionic solutions are good conductors of electricity. There are two statements. Options are simple: one only, two only, both one and two, neither one nor two. What would be your answer? You do know first statement was wrong because they have high melting points. Second one was easy, right? So some questions like this can be created. Right. Next, we'll talk about metals. Now we understood ionic compounds and our focus is on metals itself. How do we extract metals, or where do we find metals? First of all, we do know metals are found in earth crust. Now many of the metals can be found in dissolved condition in our ocean water. Now ocean water is a source of many of these salts, and from the salts we can get these metals. So what do we find? We find metals in form of minerals. Minerals how? We find metals in form of minerals which are dissolved. Example being sodium chloride, calcium chloride, magnesium chloride. They dissolve in water. We find many such stuff in our ocean water. But minerals which can be exploited easily, they are called as ores. So what is a ore? Ore is a mineral itself, mineral of a metal which can be exploited economically. So ores are found in earth crust. So mineral and ore, they are very similar. Please remember, elements, metals or metallic elements, they are not found in pure form in earth. Now except for some, say for example, I might find gold in pure form. Gold can also be found in ore form. Gold can be found in pure form. Silver, again, I can find silver in ore form also, maybe in pure form also. Platinum, I'll find it in pure form itself. So such metals can be found out in pure forms. So metals can be found out in pure form. Very few exceptions like gold, silver, platinum. Other metals, they can be in form of minerals dissolved in water. They can be in form of minerals which can be exploited exploited profitably, they are called as ores. All right, ores. Now, ores. Now, what ores do we find? What ores do we find? As I told you, gold, silver, platinum, copper. Copper also, I can find them in free state, but others I do not find in free state. I find in ores, the metals at the top of the activity series, like potassium, sodium, calcium, magnesium, etc. These are in mineral forms, and they are never found in free form. They are found in form of salts in minerals which are dissolved in water, or they can also be found in form of different ores, the solid ores on earth crust, which can be exploited, right? So now the question is, sir, what are the ores of different metals? Questions can be formed on this as well. For instance, sodium, chili saltpetre, it has sodium. For aluminium, the most exploited ore is bauxite, but you also have corundum, feldspar, alunite, kaolin. Potassium, for potassium you have saltpetre again. For magnesium you have magnesite, dolomite. Now dolomite is something from which you can exploit both magnesium and calcium. Please remember this particular point. Again, for calcium you will find dolomite here, dolomite, calcite, gypsum, etc. Other important ones are copper. You have important ore of copper, which is cuprite. Silver and gold can also be found in ore forms, different ores. But for zinc, you have zinc blende. Please remember this, zinc blende is its ore. For mercury, very important, mercury can also be found in ore form, and its ore is called cinnabar. Cinnabar. Lead. Lead can be exploited from an ore called as galena. Galena. Bismuth from bismuthite. And for iron, we have different kinds of ore, and the maximum or the most exploited ore is hematite. We can also find magnetite, siderite, iron pyrite, etc. For uranium, we have pitch blende. Please remember this, because these are some peculiar ones. I would appreciate if you remember pitch blende. For manganese, you have pyrolusite. You have magnet also. For manganese, you have pyrolusite. For others, I have told you galena, cinnabar, zinc blende, etc. These are something on which I can simply create some MCQs. So better remember these. Now the next question is, sir, I understood. You told metals. You gave properties, physical properties of metals, chemical properties of metals. Then you also told metals and non-metals, they found some ionic compounds. And then you spoke about ores. Now I am interested in exploiting these ores to get my metals. How can I do it? How can I do it? See, exploiting a metal from its ore, it depends on its reactivity. If they are highly reactive, like potassium, sodium, calcium, etc., then you need electrolysis for it. If they are somewhere in the middle of the reactivity series, for example, zinc, iron, etc., for that you need reduction, and for this reduction you use coke. I am talking about iron specifically. How do you produce iron? Iron is produced by smelting of iron ore, by reducing it by using coke, high quality coke. Apart from that, if they are highly unreactive, they can be found in their purest form as well. So depending on the ore, if they are highly reactive, I go for electrolysis. If they have medium reactivity, I look at what particular ore is available, then I reduce that particular ore to its metal. And if metals have very low reactivity, then I go for roasting or calcining and then ultimately refining. So let's look at this process one by one. If a metal is low in its activity series, meaning, say, I am not talking here about gold or silver, but let's talk about mercury and copper. These are metals of very low reactivity. Now generally we find these metals of very low reactivity in form of oxides, because oxygen is abundantly available. So over a period of time we find them reacting with oxygen to form some sort of ore. So how do we reduce it into, or how do we get metal from it? By simply heating it. When an ore of these is heated in the air, first it is converted into its oxide form, and then slowly we can get that metal. For example, mercury in its ore form is available in the sulfide form, right? So mercury and sulfur, they combine. So when I burn it in presence of air, it first leads to formation of oxide. When I burn it further, it leads to formation of that particular metal. Similar is the case of copper. You have copper in form of a sulfide ore. I burn it in presence of oxygen. First, I get copper oxide. I burn it further. I heat it further. Then I get copper. So for metals with low activity or low reactivity, I simply heat them in presence of oxygen. First, metal oxide is formed and then the metal itself is obtained. Now, when we look at extracting metals in the middle of the activity series, this process is a little nuanced. When we talk about metals in the middle of reactivity series, we get examples of iron, we get examples of lead, zinc, even copper for that matter. Now, why this process is a little nuanced? Because these metals, they form ores in form of sulfides. They form ores in form of carbonates, meaning these metals are available as ores in sulfide form, in carbonate form. Of course, they are also available in oxide form. Now, we have already established that if an ore is available in oxide form, I can reduce that to the metal form easily. Now, here, what we do, if an ore is present in sulfide form, first I have to convert that into oxide form. The classic example being zinc sulfide ore. And for this, we use a process called roasting. So for a sulfide ore, we use roasting process. Now, what is roasting? Roasting is simply heating in presence of excess air or excess oxygen. Please remember, roasting includes excess use of oxygen because I need zinc to react with oxygen so that this sulfur is expelled out. So I get zinc oxide first. By roasting, I convert a sulfide ore into the oxide of that particular metal. Similarly, if a metal is available in carbonate form, say another example, zinc carbonate. Now for this, I already have oxygen in this. Now what do? I calcine this. I subject this zinc carbonate to the process of calcination. Now what is calcination? Simply heating it in limited air. I heat this in limited air. Now what will happen? This will then transform into ZNO, that is zinc oxide. So if it is a sulfide, I roast it, convert it into oxide. If it is carbonate, I calcine it, I convert it into oxide. And once I get the oxide of that particular metal, zinc oxide, then I reduce it. How do I reduce it? By using a reducing agent. Now for these, I need a reducing agent. For metals with low reactivity, I simply heat it. I do not need any sort of reducing agent here. They can be obtained directly. But here, I need a reducing agent. And what is the classic reducing agent I use? I use coke. That means carbon coke. You must have heard the smelting of iron ore. Iron oxide. For reducing it, we use carbon coke. So carbon coke is used in the furnace. Now we obtain that particular metal and gases are released. Carbon monoxide and carbon dioxide. So either we go for a reducing agent or we can also go for some sort of displacement or replacement reaction. That is also possible for extracting metals which are in the middle of the series. Now, if they are in the middle of the series, I want to replace or displace them with the metal which is in upper sequence. I have seen in the reactivity series, whichever is higher, that is going to replace the lower one. So if I want to get say a metal manganese, from manganese oxide I want to get manganese. So how can I get it? I can displace, I can replace it with aluminium. I can displace with aluminium. Now what will that reaction run like? I get manganese, then Al2O3 is formed, and along with it heat is formed. This can also be one of the examples. So manganese dioxide is heated with aluminium powder to get manganese. How? Aluminium replaces that manganese. And one such reaction is also used to get iron. Iron is also reduced using aluminium because aluminium comes higher in the reactivity series. So if I have Fe2O3, I simply take aluminium here and I try to displace iron with aluminium here. Now this reaction, it gives extreme amount of heat. If I simply burn this aluminium, I get extreme amount of heat where I get iron, and that aluminium displaces iron to form Al2O3 and a lot of heat is released. Now in these exothermic reactions, we use them in many applications. One of such displacement reaction, one of such exothermic reaction is called as Thermit process. You must have heard of this Thermit process. Thermit process is classically used to fill the gaps between the railway tracks. Now this personnel here is using the thermit process itself. Now how do you proceed with this thermit process? In this thermit process, we create we get aluminum oxide slag. After the reaction, aluminum is burnt, and this iron, it gets molted. Iron is formed, iron is molted, and it gets into the gap between the two iron railings, and I simply cut this. Now whatever excess is there, this is filed, this is cut off, and I get two rails which are joined. So a simple MCQ can be created. Thermit, this is also called thermit welding process. If you're a mechanical engineer, if you're a mechanical engineer, you'll know about that thermit welding process. In the thermit welding process, I use this particular reaction itself, Fe2O3 plus aluminum. A lot of heat is generated. Molten iron, it gets into this particular gap, and this is welded. Thermit welding process. So we spoke about how to extract metals of low reactivity, how to extract metals in the middle of the activity series, and the third one is how to extract metal which are at the top of the reactivity series. Now since these metals are at the top, that means they are not found in the free state. They are highly reactive. Examples being calcium, sodium, potassium, etc. Now since they are highly reactive, can we use a reducing agent? Now till now, for the low reactivity, for the middle reactivity, what we did, we simply heated them in the presence of oxygen. We also used some sort of reducing agent like coke for the middle ones. Can we do it? No. See, if we go for reducing, what will happen? These metals, since they are very reactive, they have more affinity towards oxygen than carbon. So I cannot reduce them. So what do? How do I obtain these metals like sodium, magnesium, calcium? I subject them to electrolytic reduction. So what do? I take their chlorides. Say I take their ore, say chlorides, molten chlorides. I subject them to electrolysis. So what happens when I give electricity to it or EMF to it? At the cathode side, I get the metal itself, and towards the anode side, the gas is released. So I get these metals. Similarly, for aluminium, I use electrolytic reduction of aluminium oxide. So for the most reactive metals, I perform electrolytic reduction. But in any of the cases, say for metals obtained of low reactivity, for metals of middle reactivity, for metals of top reactivity or top activity also, when I extract them, they are found mostly in impure form, whatever extraction method I use. So for that, how to purify these metals? I use another process called electrolytic refining. So how do I perform this electrolytic refining? Now in the electrolytic refining, I use a pure metal strip as cathode. So one of the electrodes is pure, cathode is completely pure, and anode is the impure metal that I have obtained. I have impurities in it, and in this electrolysis process, when I apply EMF along with the electrolyte, what happens? Pure metal pure metal is displaced from the cathode side, and equal amount of pure metal is also displaced from anode side. It enters into the solution, and the impurities, they settle at the bottom. They are called as anode mud. This is a classic example of how do I purify copper through electrolytic refining. I use pure copper as cathode this side, impure copper which I obtained from the extraction this side, and I used acidified copper sulfate solution. So I get pure copper from here. All right. So we understood how do we extract metal from the ores. Now, when I talk about these metals have to be protected. Why? Because metals, they corrode. So corrosion is a process wherein metal, when exposed to moisture, that means humidity, when exposed to air, when exposed to water, or when exposed to acid, it slowly and steadily corrodes. A layer of oxide is formed over the metal, which ultimately weakens this metal. And in our day-to-day life, we have seen so many of these examples with iron. We have seen something called as rust. So iron undergoes rusting. Iron oxide is formed. A reddish layer is formed on the iron, which makes iron. It is also called cancer for iron. There are also metals like silver which get oxidized, which corrode slowly. When exposed to air, they slowly form a coating of silver sulfide. Similarly with copper when with moist carbon dioxide in air, it slowly loses its brown shiny surface and a green tinge is seen. This you must have observed also if you have some sort of copper utensils at your home, or say copper utensils especially around the temple areas, you must have seen them turning into greenish. That's corrosion itself. Another classic example is iron. When exposed to moist air for a long time, it undergoes rusting. An oxide layer is formed. So corrosion is basically formation of an oxide layer over the metal. In many cases, it leads to deterioration of these metals. And the question is, what does this corrosion depend upon? There is a classic experiment here that if you take iron nails in water where air is also present in this test tube, you will see that these nails, they undergo rusting a lot. They undergo rusting. But when you take distilled water and you separate air from this water, you use a layer of oil to separate air from this water, and now this is distilled water. Remember, it's pure distilled water. In pure distilled water, iron does not rust, especially when it is separated from air. That means oxygen will not enter this water, so it is not going to oxidize it. Similarly, if I simply keep iron nails in a test tube and I use anhydrous calcium chloride, which is a drying agent, that means it is going to suck out complete air. This air is completely dry because this calcium chloride, it takes out complete water from the air. So you will see that these nails will also not rust. So for rusting or for corrosion, I'm using the terms rusting and corrosion interchangeably. For rusting and corrosion, you need air. That means you need oxygen. You also need moisture. But in general, corrosion, it depends on many factors. Corrosion depends on the internal factors of the metal itself. It also depends on external factors. External factors can be environmental factors, or they can also be chemical factors. Let's delve a little deeper on this, because MCQs can be created with respect to this. Say if I ask you a question, rusting would be more towards mainland area or rusting would be more towards coastal areas of India, what would you choose? Right? Just ponder over it. You'll get the answer through this discussion itself. See, I told you corrosion, it depends on internal factors like reactivity of the metal. If the metal has high reactivity, there are higher chances of corrosion. If there is some chemical content or some sort of chemical impurities in it, there would be higher corrosion. If there are imperfections and residual stresses in it, corrosion would be higher in such cases. Similarly, corrosion also depends on external factors, especially environmental factors. Optimum temperature, humidity, and pH, they play a very important role in corrosion. Acidic pH leads to more corrosion. Higher temperature leads to more corrosion. Higher humidity leads to more corrosion. That is why you must have seen, especially in the coastal areas. In the coastal areas, you will find temperature and humidity factors leading to more and more corrosion. Have you observed it? If you live in coastal areas, you must have seen that metal benches, or say steel benches or iron benches that you have along the coast or along the beaches, they would undergo severe corrosion. Apart from that, there are some other chemical factors also. Meaning, for some metals, the nature of the oxide that is formed on the top, it decides whether it will corrode more or not. Classic example being, say, aluminium. See, for aluminium, when it reacts or when it undergoes corrosion, it reacts with moisture in presence of air. So it leads to creation of a small oxide layer, Al2O3, aluminum oxide layer. Now this aluminum oxide layer is highly stable. In fact, this oxide layer, it protects aluminum from further corrosion. But for others, this does not happen. So the nature of the oxide that is formed, it also decides whether the corrosion would be enhanced or whether the corrosion would be reduced. For metals like aluminum, the oxide layer which is formed on it, it acts as a protective layer. But that is not the case with iron. Apart from that, impurities. If there are impurities, impurities outside, or if there are impurities on the metal itself, it leads to more and more corrosion. It enhances the corrosion. As I told you, corrosion of iron is like cancer. So how do we stop it? We need to stop it, right? We need to stop corrosion. We need to stop that rusting. How do we stop rusting or corrosion of iron? Rusting can be prevented by painting iron. Simply paint it. That means you cut off the connecting link between iron and its environment. You cut off the link between iron and water, iron and air. Or you go for some sort of oiling. You apply oil in it. You saw this example. Simply cut off iron from air. Rusting would be less. Or you go for greasing, you apply grease, same thing. You galvanize it, you apply a layer of zinc over it. You go for some sort of chrome plating, you go for electroplating, you anodize. If you anodize iron, then the rusting would be reduced. This concept of anodizing is very prominent. If you anodize the iron, especially in water, in oceans, whenever a ship is traveling, the ship is basically converted into anode with respect to the oceanic water, where the rusting would be reduced or corrosion would be reduced. Or you can also make alloys. Classic idea. How do you do it? You have iron. Now, if iron undergoes rusting or corrosion, I add some other things to it. For example, I add nickel into it, I add molybdenum into it, I add chromium into it, so that I change its property. I create a stainless steel out of it. So alloying is a very good method of improving the characteristics or properties of metal. We get desired property from this particular method. That's why you see pure iron, it undergoes rusting or corrosion a lot. But on the other side, stainless steel, does it corrode? That's why you have stainless steel equipment, stainless steel utensils at your home, not iron utensils. They are stainless steel. Stainless steel is an alloy of iron. So I hope you have gotten a very good idea regarding metals, non-metals, and other properties connected with it from this chapter for NCERT class 10. Let me end this discussion with a couple of questions and some FYI for you. First, let me take you to the questions and then we'll talk about FYI, because those FYI, that means for your information, they are very interesting. Some questions can be created on the basis of reactivity. For instance, I would say this is a moderate kind of a question. Okay, moderate kind of a question. I can even say CSAT kind of a question. Okay, metal A can displace metal B from its salt solution, but cannot displace metal C from its salt solution. So three metals have been mentioned. Metal A can displace metal B, but cannot displace metal C from its salt solution. And metal B can displace metal D from its salt solution. So based on this particular information, you have to answer, or you have to arrange these metals in the decreasing reactivity. That means the highly reactive metal should come first and the least reactive metal should come last. Okay, do try to attempt this. I have put it in the moderate category. I would say this is a little moderate to tough question itself. You will get the answer for this question on my Telegram channel at Rahul Sai 222. I'll also put it on my Instagram with the same ID, right? Apart from that, this is an easy question. This is a very easy question. Consider the following statements. Malleability, property, malleability and ductility, its definition is given. You have to find if the definitions are correct. Options are easy. 1, 2, both 1 and 2, neither 1 or 2. This is an easy question. This is a very easy question, right? So such questions can be created. In fact, I can create so many questions from this particular chapter. Now, let me end the discussion with some FYI. Very, very interesting, because it will give you an insight into how you use your science and technology knowledge or your NCERT knowledge into your other subjects. Now, I told you that gold and silver, they are noble metals. They have very low reactivity. And that's why we see gold does not react much even with acids. But there is a solution called as aqua regia. Aqua in Latin, it means royal water. Aqua regia is a mixture of two acids, two concentrated acids, that is HCl, hydrochloric acid, plus your nitric acid. These two mixtures are called aqua regia, and this aqua regia can dissolve gold. It can dissolve gold. It has the ability to dissolve gold and even platinum. right? So they are concentrated. Beware, do not try to experiment at home. Now, apart from this, there is one more information. This is the information about the iron pillar, the Mehroli iron pillar near Qutub Minar. It shows India's metallurgical prowess right from the medieval times itself. Now, this medieval tower, this iron pillar, it weighs about 6,000 kg, right? And it is about 8 meters high. And till today, we do not see that it has rusted. So it has got some sort of rust resistance. Scientists have been examining it to understand. So a very interesting snippet it is found here. How do you use it? Say, if I ask you a question related to means that the Gupta age in Indian medieval history has been dubbed as the golden period. You have to explain, or you have to elucidate, give some inputs regarding that. So you have many other pointers like their temple architecture, their business, etc. But one of the pointers can be their accomplishment in science and technology, their accomplishment in their metallurgical development. This clearly shows the prowess in terms of metallurgical development from that particular period. All right. So you have to connect things like this. It's a small snippet more to know in the NCERT itself. The iron pillar in Mehroli near Qutub Minar. It is a work which is built almost 1600 years back. So approximately, to go back somewhere around 300-400 AD, right? So you need to connect your knowledge, something like this. All right. So that's the end of today's discussion. I hope it was interesting and enlightening for you. And if you have liked that video, you can always follow me on my social media handle @Rahul Sai 222. Thank you for watching this video. Jai Hind.